I'm going to present the work already named. This work was developed by my PhD student Fernandes, that yesterday done a presentation about cracked growth rates. This is the part of the cyclic plastic behavior. And were developed by Professor Jesus, Ricardo Branco, by myself, Costa, and Martins Ferreira in Coimbra University. So, the outline of my presentation will be some motivation and goals, some experimental procedure, the results, and some conclusions. As all you know, we are here in this section all talking about additive manufacturing. It has some advantages. It's was a promising technology 10 years ago. Now some problems arise, and these problems are mainly due to the parameter sensitivity, the isoperficial roughness, the thermal stresses, and the microstructural heterogeneities, like cavities, poros, unmelted particles, and contaminations when we produce this kind of materials. And this, combined with cyclic loading, take us to fatigue failure. That's why we are talking about this. In case of this aluminum alloy, it's important for the aerospace industry, like Raj told us yesterday from Australia. And we intend to analyze the cyclical formation material, the behavior, and the monotonic properties, taking into effect the heat treatments, the standard and non-standard routes. So we used a specimen produced by J.A.M. The building direction is the vertical direction. The standard specimen by the STM. We used the maximum power of 315 watts, 30 microns of layer thickness, and a scan speed of 1.8 microns. Here we have the chemical composition. Mainly this alloy has 10% of silicon and balance of aluminium and small other amounts of other elements. So we tested 5 cases: the as-built condition, not heat treated; the stress relief one, because why this 2 and 3 conditions? Because the manufacturing persons that do this kind of produce the machines to do this elements generally tell us to do these 2 treatments. However, we noted that these 2 treatments are prejudicial to fatigue. So we tried to introduce new ones: the HEAP, 250 degrees and HEAP, and 215 degrees, and with quenching in water. So we done low cycle fatigue tests, 13 tests for as-built, 11 for stress relief, 9 for T6, 11 for HEAP, and another 11 for 215, trying to cover all the spectrum. We done it in a constant strain ratio with a fully reversed of -1 and a constant strain rate also. So some results. Here we can see the microstructure of a as-built specimen is typical of this kind of AM materials. We have basically 4 zones. We have the zone 1, the interior of the melt pool, fine cellular microstructure. We have the zone 2 here, the boundary between the 2 melt pools, where there is also a cellular coarse microstructure. Then zone 3, cellular coarse microstructure due to localized cycles of heating and cooling. And finally, a dendritic columnar substructure caused by the melt pool solidification direction. In general, it can be said that the as-built series is mainly composed by a supersaturated aluminium silicon cellular dendritic microstructure. This left figure presents the microstructure after the stress relief heat treatment, and this one is the ADX analysis for the T6 condition. The application of a residual stress relief heat treatment and T6 cause microstructural transformations, which is characterized by silicon precipitation from the supersaturated matrix, resulting in a reduction and substitution of the matrix supersaturated with aluminium and silicon phase by spheroidal silicon in the aluminium matrix. You can see this spheroidal silicon particles here and the matrix of aluminium. So we don't have fine particles, but the silicon is aggregated, and then we have the aluminium part. The same happens here for the D6E3. Sorry, the same happens here for the D6E3. So finally, the microstructure for the treatment of 215 degrees and then quenched in water, and this non-standard heat treatment provoke homogenization and thickness in the aluminium cellular microstructure that will be reflected in the further results. So this is the hardness comparison between the 5 cases, and as expected, the substitution of the matrix supersaturated by the aluminium silicon phase of the heat, consequence of the heat treatment, caused the hardness reduction, with the worst case being the T6 condition. So the T6 condition is the worst case. We have more sphericalization of the silicon particles than the stress relief. When we pass for the non-standard tests, although the hardness is lower than for the as-built, the loss of hardness was lower than for these 2 treatments. And the heat treatment compared to the 250 treatment, they are made by the same temperature, but the heat treatment has 100 megapascal pressure, have no hardness change, significant hardness change. Comparing the monotonic tensile tests, the difference in hardness is reflected in this figure. We can see that the T6 condition has the lower yield stress than the stress relief. Then the other 2 non-standard tests are more close to the as-built condition, although there is a decrease in the yield stress, but the strain at rupture is increased, the ductility is increased. That is reflected in the cycle stress strain response. Here we can compare the 5 cases for a strain amplitude of 1.25%. And we can observe that the heat treatment, mainly the stress relief and the T6, reduce the linear part of the hoops. This has a more increased linear part, this linear part is more reduced for the 2 heat treatments. And the fatigue was higher in this case for the stress relief condition. When we compare the stable stress loops at midlife for all the 5 cases, for also a strain amplitude of 1.25, the same for lower stress amplitudes, delivers a large difference in the form of the stable stress loops in these cases. The linear part of the loops is reduced, as already said, and the stress relief T6 condition have more significant reductions of the linear part than the HIP and the 215 degrees treatment, which indicates a clear reduction of the hysteresis circuit area and also of the associated plastic deformation energy density that we'll see later on, exposed in the graph. This compares the stress amplitude with the number of cycles. We can see that the transient behavior is relatively smooth for all cases. However, we find and can identify different cycle strain responses. The as-built and the stress relief conditions exhibit a mixed behavior, hardening response at higher strain amplitudes and softening at lower strain amplitudes. We will see in the next graph, because in the next graph we have for a lower strain amplitude, this one. You can see there some softening here. And here we see hardening. And the T6 condition exhibits always hardening, and the HIP and the 250 condition shows a softening behavior irrespective of strain amplitude. Also, one hardness, the other one always softening. When we compare the normalized, this is for the lower stress amplitude, this is for a stress amplitude of 0.5. We can see easily that for the 5 deformations, that for high deformations hardening is observed, and for the lower strain amplitude softening is observed for as-built and stress relief. When we put it in form of dimensionless life, we can see that the amplitude variations occurs at very early stage, only for the first 2-3 cycles, then a saturated state is reached in all cases. The cycle strain curves were obtained. They coincide with the hysteresis loops, except for the compressive part of the non-treated specimen. When we try to see the macing behavior, they have not pure macing behavior, but for the 4 treatments it is very close, so we can use the macing curve, but for the as-built specimen there is no following of the master curve of the macing curve. Finally, the strain-life relations were obtained for all cases and compared with each other, and the better comparison is to see the plastic strain energy versus the number of reversals to failure. In this figure, this is shown, and we can see that generally there is a good correlation between plastic energy density and fatigue life, so the predictions are correct. In this case, a bilinear function on the log-log scale fit well the data, basically in the high lives. For lower lives, the heat treatments do not significantly affect the energy life. Nevertheless, the higher fatigue lives, the trends are relatively different from case to case. Finally, we can plot the total strain energy density versus life relationships, and in this case, the density is less affected by the material conditions. In addition, the results are relatively close to those found for the as-built condition, fitted by the dashed line, the dashed blue line. This dashed blue line is for the non-treated material, and the other ones for the treated materials. So, finishing, drawing some conclusions, the aluminium silicon 10 magnesium manufactured by selective laser melting is very sensitive to the post-processing heat treatment, either under static loading or cyclic loading. All post-processing heat treatments increase ductility and reduce strength when compared to the as-built condition. The stress relief and T6 led to highest ductilities and lower strengths. The HIP and the 250 led to intermediate values, increasing ductility without significant reduction of strength. The T6 condition exhibit the hardening behavior, while the as-built and stress relief condition show the mixed behavior. HIP and 215 degrees exhibit the softening behavior. The plastic strain versus life relationships and also the strain-life relationship were characterized by bilinear relationships on the log-log scales for all tested cases. Plastic strain energy versus life relationships were successfully fitted using bilinear functions on the log-log scales, of course, and the fitted functions were affected by the material conditions. I hope I conclude my time. Thank you very much.
So we have time for 1-2 questions, please.
Thank you for your presentation, Professor. I have one question. Have you some explanation why the tensile strength and hardness decrease with the heat treatment in this?
Yes, that was, I don't explain it very well here because I have no time, but there is a work of Yoshi that tells us that until the separation of the silicon particles is at 2060 degrees. Cycle, you have a different composition, you have a different microstructure. So when you make T6, it's at 550 degrees, and we make the stress relief that the manufacturers tell us is 300 degrees. So at those temperatures, the silicon separates from the aluminum matrix. So that's why we try to do 2 heat treatments with a lower temperature, and we have got better results. Yes, but we have to try it. This is just an ongoing project, and there is a lot to try to understand at the moment. Thank you for your question.
Thank you.
Any other questions? Please.
Yeah, could you show your the last slide? Spray energy. Could you show the last one?
This one?
Yeah. I just have a quick question. For the spray energy, you calculate the elastic part. You add another triangle there. And why you don't add the triangle for left-hand side here?
No, sorry. This is the total, is the elastic and the plastic.
Yeah, but your figure there, the last.
Oh, the figure is not, it has a problem here.
You mean you
Yes.
have already added this?
Yes.
Great.
It's correct, it's correct. Thank you for your analysis.
Any other questions? Well, we have time for just one.
Okay.
By me. Did you measure the residual stresses in the
No.
as-built condition? Okay.
No, that's the next step
Okay.
that we have to do, because it's very important, not here, but in the work presented yesterday, in the crack growth rates, we didn't notice any influence of the stress ratio. So, in my opinion, that's the influence, the big influence of the stress, the stresses, the residual stresses. Because in fact, we are not doing it at the R0, but probably at the R05.
Yeah.
That's the next step.
Yeah. Okay. Thank you again.